welcome to our ocean science project. My name is Amélie.
I'm Cassandra.
I'm Vlad.
I'm Hubert.
I'm Sergey.
And behind the camera is Luke, and the rest of our group is Zulong, Hayden, Leo, Runming, and Subin.
Okay, so today we are going to talk about apex predators and how being at the top brings its own challenges. We're going to do this through food chain and maximum sustainable yield. Before we start, let's explain what exactly our critical concepts are. Food chain efficiency is the percentage of energy that gets transferred from one trophic level to the next in a food chain. It tells us how much energy flows upward from phytoplankton to zooplankton to fish to predators, and how much is lost along the way as heat or waste. Maximum sustainable yield, or MSY, is the largest amount of a species that can be harvested year after year without reducing its long-term population. It's the balance point between taking enough to use resources efficiently and leaving enough for the population to replenish itself. So these two ideas work together. Food chain efficiency explains how energy supports life in the ocean, while MSY shows how humans can interact with that energy flow responsibly. Our group's focus was on determining how do oceanic apex predators affect their environment and ecosystem. So let's dive into that and how these processes interact and connect, starting with how energy moves through the marine food chain.
Let's start with food chain efficiency, which describes how energy moves up the food chain from sunlight to apex predators. We'll start at the base, where solar energy powers phytoplankton and zooplankton, the primary producers. They're eaten by small fish, which are primary consumers. Next, those fish are eaten by predator fish, the secondary consumers, and finally we reach whales and other large marine mammals, which are the apex predators. This flow of arrows shows how energy moves upward, but notice how each step involves a loss. About 90% of the energy is lost as heat, waste, or movement, leaving only 10% for the next level. So all of the sunlight captured by plankton, only a trace ends up supporting top predators like whales or sharks. That's why apex predators are rare, since there simply isn't enough energy left to sustain many of them.
Now let's expand to see how this looks across trophic levels. At the bottom, primary producers store about 20,000 kilocalories per meter squared per year of energy. Above them, primary consumers drop to 2,000, secondary consumers to 200, tertiary consumers to 20, and finally, apex predators at the top hold only two. There is the 10%. That is the 10% rule in action, since only 1/10 of the energy passes upward each step. This is also why ocean food chains are longer and less efficient than those on land. Phytoplankton are tiny and short-lived, so energy cycles quickly and constantly. On land, long-lived plants store energy for years, which makes the system more stable. So, for apex predators in the ocean, survival depends on enormous and continuous supply of prey.
Okay, so now let's look at where in the ocean food chain efficiency is actually the strongest, which is in coastal upwelling zones. Here's how it works. So, strong surface winds push warm water away from the coast. As that warm water moves offshore, cold, nutrient-rich water from the deep ocean rises to replace it. This process is called upwelling. It acts like a nutrient elevator and brings nitrogen, phosphorus, iron up to the sunlight zone, fueling massive blooms of phytoplankton. Those phytoplankton feed on zooplankton, which then feed fish, which then feed apex predators. And even though upwelling zones only make up 2% of the ocean surface, they produce over 50% of the global fish catch. They're like underwater farms with short food chains, high energy transfer, and thriving predator populations.
Now, sometimes these upwelling systems break down, which is what happens during El Nino events. Under normal conditions, trade winds push warm surface water westward across the Pacific, allowing cold, nutrient-rich water to rise along the coast of South America. But during El Nino, those trade winds weaken or even reverse. Warm surface water flows eastward instead, covering up the cold water below and blocking upwelling. Without nutrients rising to the surface, phytoplankton production plummets, small fish population decline, and apex predators either migrate or starve. So, El Nino perfectly shows how sensitive the entire food web is to changes in nutrient flow, as one disruption can ripple through every level, all the way to the top.
Now let's connect this back to our apex predators. Species like sharks, orcas, and large tuna sit at the very top. If humans overfish their prey beyond MSY, predators lose their food source. And if predators themselves are overfished, the entire system can unreveal. Without top predators, mid-level species overpopulate, devour lower levels, and cause what we call a trophic cascade. That's why protecting predators and managing sustainable yields go hand in hand, since both keep the oceans balanced and productive. So how do oceanic apex predators affect their environment and ecosystem? They're the balancing forces of the ocean. They regulate prey populations, maintain biodiversity, and recycle nutrients through moving and feeding. When we combine both concepts, the pictures become clear. Food chain efficiency shows how energy flows up the food web and why predators are so few, while maximum sustainable yield shows how humans can harvest without breaking that flow. And when upwelling and nutrient cycles work as they should, the entire system from plankton to whales thrives. But when El Nino or overfishing disrupts those flows, the pyramid starts to crumble from the top down. Apex predators may be few, but they're the key to keeping the ocean alive and balanced. Thank you for taking the time to listen to our Chalk Talk. We hope you learned a lot about food chain efficiency, maximum sustainable yield, and the importance of oceanic apex predators in our waters.
Now that we understand how energy moves naturally, let's switch to the human side on how we can fish without destroying the system. So when fishing increases, the size of the fish stock goes down, and when there are fewer fish competing for food, the ones that remain actually grow faster. More food for each fish means a higher production rate in the population. So here is a graph which shows this. So when the fish stock is very large, there is a lot of competition for food. Growth and reproduction per fish is low. As the population decreases due to fishing, then more food becomes available per fish, individuals grow faster and reproduce more, so the rate of reproduction increases. So, now, as fishing effort increases, the amount of fish harvested, aka the yield, also increases, as you can see here. However, if fishing effort keeps rising, it begins to push the fish population down too far. So beyond this peak, increasing fishing effort actually causes yield to decrease. You're working harder but catching less fish. So what does it mean? Eventually, we reach a point where the population's reproduction and growth rates are just enough to balance what's being removed from both fishing and from natural predators. This tipping point is called the maximum sustainable yield. So if fishing increases even a little past the MSY, the population can no longer keep up, it begins to collapse. So why is the MSY hard to measure? Determining the MSY is difficult. There are too many factors that can shift it. For example, climate change, ocean temperatures, diseases, outbreaks, and environmental disturbances. So understanding the maximum sustainable yield is essential if we want oceans to stay productive, ecosystems stay balanced, and fishery to last for generations.
After our presentation, our group has come up with 4 critical questions that relate to our 2 critical concepts. The first one is only about blank amount of energy is passed from one trophic level to the next, in the ocean food chain. Our second critical question is where in the ocean is food chain efficiency the highest? Our third critical question is what does maximum sustainable yield represent? Our final critical question is why should fisheries harvest below the MSY instead of right at it?